All right. So what I want to start talking about today, so we've talked about free modules, right? Free modules make linear algebra easy. If you have a free module over rings, right, some number of top of the ring. Let's look at some other types of module. So I'm going to define these notion of projective and injective modules, and they're kind of twins of each other. They're mirror images of each other. They're dual notions. And you will notice I'm going to define projective modules and I'm going to define injective modules. And for almost all the theorems we have, you'll have some theorem for projectives and you'll have sort of an analogous theorem for injectives. So let me write this way, definition. 661. Consider the following diagram of R modules with bottom row exact. R module homomorphisms. Where bottom row exact. So here's the diagram. So all this really means, of course, is that G is on 2. We'll call this P, and we'll call this F. We say that P is projective. There exists H from P to A, such that when you do H, okay. So given this any diagram here, any F, any G, as long as G is on to, we say P is projective if it's created. You can find a H from P to A that makes the diagram move. So another way to think about this is you think of B sort of as a small, right, relative to A, because this map is onto it, right? So projected is given a homomorphism from P to the smaller one. You can lift this homomorphism from P to the larger one. Right? So you can lift this homomorphism F up to the preimage of B, such that this diagram can use. So that's what it means to be projected. So given this, you can project onto this picture. Right. Okay. Now there's a dual notion. Consider diagram of R module homomorphism with top row exact. And in this case, here's my picture. Again, Jim. We say I is injective if there exists H, B, and I, such that when you do G, then you do H. So this time it's kind of a mirror image. It works this way. G, H, I. So think this way, when the injective is, I think you can think of A sort of as a submodule of B, right? This is one. If you have a homomorphism from the submodule into I, then you could always lift it up to a homomorphism from the bigger module. For most nice rings that you have, this is like really sloppy to say, but in a certain sense, it's easier to find projectives than injective. And I consider projective sort of more important. That doesn't mean that injective is not without its charm and value. But let me give you kind of the first theorem, and then we're going to do some dual stuff here. Well, I'm going to do kind of a projective, and then a projective standing alone, and then injective standing. And this is a big one, and this is why it's easy to find projective modules. Theory. Every three R module is projective. And so all of a sudden, we have a boatload of examples, right? Of course, I think part of the burden in the future will be for us to find a projective that isn't free. Because after all, what an idiot I would be to do all these definitions and stuff if they're equivalent to free. What a waste of everybody's time, right? That's why examples are important. But for now, we'll just kind of move ahead. I want to show that if you have a free module, it's projective. So let's set up the diagram. Suppose we have and this is my free R module. Now let's suppose that F is free on the set X. So think of X as the basis, right? Well, X is my set. And since this is free on X, of course, a free module is free on subset. And by the way, I'm assuming it does have a basis. Let me point out that the zero module, you can always complete this diagram with zero homomorphism, right? So if your free module, if your free module happens to be zero, you're good to go here. It's projected. But we'll assume it's got a non-empty basis here. If I goes from X to F, since G is on to there it is. There is an AI and A such that G of AI equals iota F xi. Okay, so let me kind of explain what's going on here. So xi, my notation here, xi is in my set. So I think of iota xi as one of our basis elements. So what I'm saying here is if you have xi, iota xi is in F. And when you push it down here, you get F iota xi, right? I don't know much, but it's something down here. right? Because I've got this out given. And all I'm saying is there's an AI that goes here. Because after all, this mountain here is onto, right? So we have a function. We'll call it capital F. Oh, that's terrible. We'll call that star. When X into A. Such that this gives me a function from X into A, right? Start with my X, Xi. Do iota to it, it goes down here, and then find the same that goes on to it. By the way, I built this function using what? What's that? Well, so here's kind of the problem, right? I'm using the axiom of choice here, right? Because what I'm doing is I'm taking Xi in here. Iota puts it in this, now push it down here. This is a well-defined element. However, I expect there to be many in general AIs that go here. And so I'm actually, to define my function, I'm using the axiom of choice, right? Because given that Xi, I look at it, I'm picking 3 in here. Everybody good with that? But it does give a function, input Xi, output something here. And since F is free, this induces a homomorphism. I'll probably keep in notation. F star R from F into A. With the property that F star R iota is equal to F. F star here. And notice that F star bar iota Xi is equal to G of AI and so in particular, when I do G and F star bar, I get F. Well, which equals this. This is F iota Xi. So when I do G, F star bar G, and this is, I guess I call this F star bar. So in particular, F is projected, or right, F is projected. So any free module is projected. Instead of coming up with an example of a free that's not projected, or I'm sorry, a projected that's not free, I'm going to develop some stuff first. But before we get into that, let me do kind of an analog for injectives. And I'm not going to go all the way to the weeds of this. I'm just going to do a little bit. How many of you all have ever heard of a divisible group? Let me be an abelian group. we say P is divisible. But if we're all D and D and in let's say natural numbers, fine. There exists D prime and D such that in D prime is equal to notice, okay, so I'm gonna be kind of sloppy about this, but notice this sort of means that what this means is for every natural number and every D in the group, you can divide by n. Right? That's essentially what it is. Anybody give an example of a divisible ability group? An ability group where you can basically give it any natural number, an element of the group, that natural number divided by, and it's still a group. Right. Uh, X. This is a ability group. By the way, every one of those groups I wrote up there has the property that every element has infinite order. Do I agree with that? Anybody give me an example of divisible with the middle for every element that's finite order? The problem with C mod n is you're gonna have a hard time dividing by n. Right, so how about C mod 2? Can you divide 1 by 2? That's gonna be a problem, isn't it? How about this? Is it clear? This is divisible? Because given the coset Q plus N, we've certainly got Q over N plus 3. All right? So you can divide everything by N. By agree? And everything in here has finite order. Can you tell me why? A typical coset looks like this, right? If you add that to itself many times, you get A is in C is 0. So the order of this is B or less. Right? If it's a fraction, for example, not reduced. Okay, so there's some examples of divisible groups. Why do I bring this up? Am I having a stroke? Well, maybe, but there is a point. Lemma 665. D is divisible if and only if D is an injective Z module. Right, so what this limit does is, I'm not talking about injectives in general, I'm just limiting this to abelian groups. So D is a divisible abelian group if only if as a Z module as a abelian group, it is injective. I am only going to do this direction. I think the other is an exercise. So why is it the case that if you're an injective Z module, then you are divisible? So let D be injected as a Z module. And of course, I want to show that D is divisible, so let D be a D and N be some natural number. And I want to show that I can divide D by that N. I'm going to consider the diagram. Diagram Z modules. And this is conclusion. Right. Now, because of the fact that this is divisible, not this is divisible, this is injective. There's this, I can always complete this diagram thusly. So let's let, so by the way, let me point out that this is inclusion, so it takes every N. So a general element of this looks like N times M, and that you set the N times M here, right? Let's let uh, so if you look at N prime, oh, right. I think this one. Notice, by the way, let me also point out that this is a free module, isn't it? If I agree with that. This is because it's generated by the single element N, right? It's isomorphic to Z. It's not equal to Z, but it's isomorphic to Z. So we'll find F of N. Because I can do that with a free module, right? I pick an arbitrary element of D. My generator of the free module is N, and I just take that. Right? Now I'm going to let H of 1 equal D prime, and I'm going to show you that this works. So if you look at ND prime, this is NH1, which is H of N. So let's see, this is H of N, but this diagram has to be it. So N goes to N, and then H of N, that should be F of n, which is D. So let's isolate what we want. And I get n d. And this is exactly the result I was doing. So it's divisible. Okay, any questions thus far?
I have a question. So injective and projective means that if we are given any exact sequence, right?
Well, what,
Like those A and B, they need to end.
anything, as long as for the projective case, the map is onto, injective case, the map is one.
So, yes, so F and G has A, so.
Yeah, that's right, that's right. Okay. As you might guess, the next theorem is a real beast. And it has a companion. This is, I'm going to do these two theorems in parallel. There's a projective part and an injective part. 666 will be the projective part. Let P be an R module following or equivalent. Number one, P is projected. P is projected. Next one, every short exact sequence of the form 0, A, B, E, 0 splits, and C, there exists an R module K. This is my favorite one. Such that P direct sum K is free. So here's another way you can tell if it's projective. If it is a piece, and by piece I mean a special piece, a direct summing of free module. If you can take your projective and put it together with some other module and make it free, it's projective. Notice that this last one encompasses the previous theorem, right? Because here you can take the R module to be 0. So in other words, if P is free, P sum 0 is free. So there you go. So this sort of gives you the projective. So the frees are projective. And here is the mirror image theorem. And this one you have for homework. Let I be an R module. Following our equivalent. And I think I told you in the homework. I think I told, so make a note of this. I think I told you in this homework. I think for this one, for you proving this one, I think I told you that you can assume that any module can be embedded in an injective module, right? Which is something that might not be clear at this point. The following conditions are equivalent. One, for A, I is injected. B, every short exact sequence of form 0, I, B, C splits, and C, you don't get quite the nice splash you do from projective. I is the direct summand of any module of which it is a submodule. I J is submodule. J, then there is this K and J such that J is not something. Okay, any questions on that? We will do a proof of 666, and I will leave you all 667 without. She might have moved me to, maybe put over here as diagram so I can remember, what it means objective. It means I have, and there exists H such that, HG. So I've got that. I want to show that every short exact sequence in this form is split. So let's let 0, A, B, P, 0 be short time. And I guess I will call this G. Now, we have split exact sequences. You can show this splitting anywhere, right? You can show that there's homomorphism from B to A, such that when you do this and that, get the identity on A. There's a homomorphism from P to B, such that when you do this and that, you get the identity on B. It seems like I should probably key on this because this is where the information is goes along. Now, somehow I want to take advantage of the fact it's objective. I feel so dirty doing this, but I will do it anyway. Right? What a darkness for Orcus. Certainly I have the identity here. And notice in this triangle here, I have exactly the diagram I want here. Now, we're assuming that P is projective, so there exists projective. There exists H from P to B, such that when I do H, then I do G, I get this thing. And there you go. That's kind of cool, right? How about B implies C? I have any short exact sequence of this form splits. How can I show that he is a sum of R modules? There's another, yes, a sum of 3 modules. Any ideas?
Could we make B a free module?
There you go, right. So any R module. So P in particular is a homomorphic image of a free module. Yeah. Okay. So I have this map here. Here's my free module. Here's my P, and this is on to. Gosh, I'm so close. Ooh, don't I wish I had a short exact sequence, but I've got a short exact sequence that looks like it was once married to Henry VIII. It's missing pi. Right? So how can I get a short exact sequence out of this? I feel so dirty. Oh, gee, it's a submodule. Let's just take the inclusion map. Because this is inclusion map, it's 1-to-1. We already know this is onto. And the image of this is exactly the kernel of this, because it's the kernel of that. So there you go. This sequence splits. So what is true when a sequence splits? The middle piece is isomorphic. So there you go. It has a projective module, it's a direct sum in there. This does not mean it's free, and I'll come back to that in a moment. But let me also notice what must be true of the kernel of G. It's also the summand of a free. So this must be projective as well, right? So it's symmetric. I mean, if you think about it, there's nothing special about P. I just picked it first. The other piece, if you believe this theorem, the other piece also has to be projective. Right? Okay, almost there. Any questions? Now we need to just round it out and show that if you have a module that is summoned of a free, then it has to be projected. And so how are we going to go about that? Well, let's suppose right. So let me suppose, let's suppose P is some uh, and so we will write F. I should say isomorphic, I'm using the notation, but I know that P is the sum of a free module, so just put those two pieces together and call it F. And I know that F is free. Now, what do I need to do? Well, suppose that I give you A goes to B 0, and I've got some G here, and I have P here. Somehow, actually, so somehow I've got P here and something F. This is G and it's on to. I've got to go over here. The only thing I know about P at this juncture is it's the sum of some free module F. Right? So what did our earlier theorem say about free modules? Free modules are always what? They're always projected, right? Do I agree with that? So let's do this. This is free. Hence, projected. And let me just kind of follow my nose here and do my best. I know that there is a map, and I'm going to call it type P. And type P takes the order pair little p little k to P. Right? I can do that, right? I mean, there it is, just take out P. Right. And if you notice, in this big diagram here, there exists, let's call it H from P sum K to A. Such that when I do H, then I do G, it's the same thing as climbing all the way down the ladder. Everybody agree with me? This uses the fact that we know that threes are projective. So if I take this thing, pi p f, it goes all the way down here, I should be able, by some h, to go here. It looks like I'm closer than I am, but how am I going to get from P, to start with a P and P, and get to A? So I start here, somehow I've got to get here. Okay, let's go up. Does anybody see, what's the most natural way to go from here to here?
Use zero. And then second.
Yeah, I'll try that. P. So that. And here's an important piece of it. Well, what happens? Well, how, now that I've got this, I can get here, I'm gonna call this H bar. I'm gonna define H bar is equal to, I'm gonna do the only thing it appears I can do. I'm gonna jump up here and then I'm gonna take the slide down on H. So I'm gonna go out of P and then H. Now, the last thing I guess I want to do is, what happens when I do, what happens when I do I over P and pi P? Well, let's see. So if I do I over P, pi P, it's just ending on P. Now, check this out. Let's look at H bar and then G. Well, right, notice that, when I do H bar and G, oh, right. This is G H out of P. Right. Because that's the way I define H bar. And what do I know about GH? Well, it's that. So this is F out P out of P, which is F times UDP, which is F. So G H bar equals F. And so P. Diagram. That's cool stuff. Any questions on that? Um, let me give you a couple of corollaries of this. Any questions? Uh, Again, I'm gonna have a projective and injective piece here. Corollary, 668, I guess. The projective, kind of projective result. Suppose I have a family of bar modules. Family bar modules. Then the direct sum of PI is projective. If and only if PI for all I. So a direct sum of a bunch of modules is projective, if and only if the direct, if and only if each are module. Okay. So I can go through this proof, I think, fairly quickly. Suppose the direct sum of PI is projective. Right. Then there exists K such that K direct sum PI is free. So let J be in the index set, and notice that K, you should probably, this is fairly obvious, but you're not going to check me on this. What did that do? Notice this is free. I pulled one of them out, and notice this is a direct, this PJ is a direct sum and it's free module. And so PJ is projective, right? On the other hand, suppose each. So I'm going to do some obvious isomorphisms that you might want to check on, but let's do the other direction. Suppose each PI is projective. So for all I, there exists K sub I such that PI direct sum KI is free. Therefore, right, because each one of these is a direct sum of R, period, because it's free. And this is a big direct sum, a bunch of direct sums of R. So this is a big, and this is isomorphic to the direct sum, PI, direct sum, KI. So this is projective. Any questions on that? I'm gonna give you one quick corollary and we'll be out of here for today. But I'm going to do the injective result, which I will leave the proof as an exercise. But I's J. J is some index set. Whatever that Greek letter is, be a family of our modules. Anybody want to guess what the analog is? IJ is injective. For all I. Index set, if and only if. What? I won't guess.
And then, road.
That's exactly it. J. So think about that one and we'll pick it up there next time. Any questions? Questions? All right.